Thank you. Why is it? Oh, hold on a second. Why does it tell me to join audio? Oh, computer audio is connected, right? So it's all right. What is this? I'm not used to this. Just the way it's laid out.
That's yours. I mean, as long as you open that.
Okay, gotcha. Yeah. I'm so silly. Oh, it's Peter. All righty. Right. We got here 57. By the way, I'm recording this, so anybody let me know if you object to that, because I thought about maybe putting these on YouTube, and I certainly hope I didn't swear before I unmuted. So,
I mean, we have to accept if you're recording it anyways, so.
Oh, okay, I see. All right, that's good. That's good to know.
Nice shirt, by the way.
Okay. All right, let's see what we got here. Still got a couple minutes. Let me kind of test my stuff here. Okay, there's that. And that. All right, so we've got a handful of people here, but I want to give just a couple of minutes because we do this math class. It's kind of a different dynamic when people just have to log on, right? But hopefully down the road we've got next week is September 4th, and we do have another speaker. Felice is going to be talking, and he's always got something good to talk about. So he'll be talking next week. And oh, before we go, people coming in. Freeman, yeah. So so the rules are kind of, there aren't any rules. It's probably good to keep the sound off, you know, if you've got like dogs and cats or whatever. But whenever you want to jump in and ask a question, in fact, that's probably the best way to do it, because I'm still getting used to all this kind of Zoom stuff, and so sometimes I notice the chat when I'm like doing whiteboard stuff, and sometimes not. So,
who did you say is speaking next week?
Let's see. Next week, September 4th, isn't it? I think it's Felice, I think.
Okay, okay. It just cut out the first time you said it, or at least it did for me.
Okay. All righty. Well, this looks like a good time to talk or to start. Welcome to our first Zoom Pizzaless Math Club. I can't wait till we can all get back together and eat together without worry of getting cooties and whatnot. But what I'm going to talk about is I'm going to talk about finite fields and their relation to quadratic forms and sums of squares. So this is just kind of recreational. It's kind of fun. You're going to see some neat math that connects up maybe with some stuff you've seen. Don't hesitate to stop me if you've got any questions. I might try this if I do another math club talk in front of a whiteboard because I like being able to see out there a little bit better. But I don't know how well. I tried that last semester with some of my classes. I got a lot of complaints. It's hard to see a whiteboard on the camera. So I'm going to try to do this. So speak up if there's any questions. So let me start kind of from the basics. Okay, what's a field? Everybody has seen a field, whether or not you have heard that particular terminology. And by the way, I promise you, I have beautiful handwriting, but it's like a serial killer on this thing. So I'm sorry about that. So what are fields? Fields are basically speaking, they're mathematical structures where you can add and multiply, right? Now that's very fast and loose, but if you want to be a little bit math fancy, you'd say it's a mathematical structure that's an abelian group under addition. If you remove the zero element, it's an abelian group, and the addition and multiplication play together well because you've got the distributive property. We're not going to beat that dead horse too much, but for fields, most you can think of it as it's a mathematical structure where you can add, well, I'll do it this way so I can be lazy, where you can add, subtract, multiply, and divide, as long as you're not dividing by zero, right? That's essentially it. And the order of multiplication doesn't matter. So familiar fields that you guys have all seen are the rational numbers, and this one's really familiar. Probably you saw this, even though it's more complicated than the rationals. The reals, you see that in all of calculus, right? So you see these, and you know, you've got to be able to divide by everything that's not zero. So people think of, I know that I thought of fields as very large things when I first started thinking about them, but fields can be small as well. So let me give you an example. If you look at Zn, so most of you have probably seen this example, but I know there's a couple of undergraduates here today, so just holler up and yell at me if this looks kind of strange. But if you look at this ring where you do addition and multiplication mod n. So for example, if you have Z12, what you do is you add and multiply integers just normally, and if they're bigger than 12, you can basically divide that by 12 and get the remainder to get the result. So it's like going around a clock, right? If you're in Z mod 12 and you add 11, if you add 3 to 11, think of it this way. If you're out at a party at 11 o'clock and you don't come home for 3 hours, you don't come home at 1400 hours unless you're in the military, it cycles back around to 2 o'clock, right? So you can, this is a mathematical structure where you can add and multiply, but for some values of n, this can be kind of strange because if you look at Z6, let's say NZ6, 2 bar times 3 bar, 6 bar, and 6 bar is where you start the clock over. And boy, that's kind of strange because you're not used to being able to multiply two non-zero things and get 0. However, if you look closely at this, I have gotten away with a cheat because basically I multiply two numbers that equal where I start the clock over again, right? How can I set things up so that this is impossible? Z, this monkey shines is impossible. That is to say, you can't get two non-zero things multiplying together to be zero, right? And it turns out, let me just look at a particular example. Z5 because of the fact that 5 is prime, like P is supposed to signify a prime here, the product of two things being a multiple of a prime means one of those two things has to be a multiple of prime. So you can't ever have this effect at the top of the page going on here. And in fact, I'll go you one further. In this example, every non-zero element has an inverse in here. So the multiplicative inverse of 1 is 1. 1 times 1 is 1. 2 times 3 is 1 because 2 times 3 is 6, which is 1 in this thing. So another way to put this is 1/2 is 3 and 1/3 is 2. And 4 is also its own reciprocal because 4 times 4 is 16. And when you divide that by 5, you get remainder 1. So 4 times 4 is 1 as well. So this is actually a field, right? Because every non-zero element actually has an inverse. So I can extend this a little bit, and I will right away. Let me give you the following theorem. 1. For every positive prime P and natural number N, there is a unique, I put this a little bit in quotes, field of P to the N elements. Now, let me make a couple of things kind of clear before we go on. That means if I give you any prime and any natural number, there is a field of that many elements, exactly that many elements. Now, you might, don't confuse this with ZPN. So for example, 1 prime is 3, and I could take the second power of it. There is a field out there somewhere of 9 elements, but it's not Z9. Z9 has the same problem that that Z6 had back here. It's not a field. You can get two non-zero things multiplying together to give you 0. How do you construct a field of 9 elements? This requires a little bit more than we're going to do in this talk here. In particular, here's what we're going to focus on. ZP is a field of P elements if P is prime. And I'll focus mostly on that. There are fields, you can extend this out to fields with P to the N elements and so forth, but that's not so important for this talk. But let me make a couple of interesting points about the way these perform. One interesting observation, which is true for finite fields, but you don't expect it to be true of fields that aren't finite, is this: if F is a finite field, and X in F is not 0, then X to the K equals 1 for some K. That's really kind of, I mean, look, if you're in the real numbers, I don't care how many times you take a power of the square root of 2, you are never going to get back to 1. In fact, that gets bigger and bigger and bigger, right? I mean, that's like a real analysis kind of thing, right? If you look at that sequence, right? But in a finite field, everything cycles back to 1, right? And actually, just because it's fun and I have nothing better to do on Friday, I am going to give an idea of why this is true. Just look at all powers of x. Now, I don't know much, but all of those powers of x have to be in my field, right? And what do we know about the field? It is finite. And what do we know about x? It's not 0, right? So if this is the thing I've got in red here is an infinite list, but it's an infinite list of crap that comes out of a finite set. So I don't know much, but it has to have repetition, right? So there's some point where it has to repeat later, right? Everybody agree with that? Right. So there have to be repeaters here. Well, so what do I get? I get x to the m plus k equals x to the m. And since this is a field and x is not 0, I can just divide both sides, because remember in a field you can divide if it's not 0, both sides by x to the m, and I get x to the k is 1. Right? So this is something that happens in a finite field, and of course finite is heavily needed there. This is wildly untrue if you have an infinite field. And in fact, I'm going to go a step further, and I will give you a tantalizing problem that might drive some of you mad. Here's a theorem. Another really groovy thing about finite fields is this. If F is a finite field, any finite field, like ZP, for example, then F has a primitive root. And I haven't told you what that is, but I will. That is to say, there exists X in F such that every non-zero element of F is a power of X. So in other words, there's this magic, actually usually more than one, but there's at least one magic element in the field that as you take the powers of it, it goes through and creates everything in the field except for 0. The proof of this is not terribly hard, but you need a little bit of stuff about equations, and you need to know, well, at least the way I'd do it is you would need to know the fundamental theorem of finitely generated abelian groups, and that's going to get us off. But you can hear me now and believe me later about that. But let me show this to you in action, and then I'll give you an open problem. If we look at C5, notice, let me look at, and I'm going to stop putting, forgive me, I'm going to stop putting little hats over this. But if I look at the powers of 2, multiply by 2 again, notice, if I look at the powers of 2, they're 2, 4, 3, and 1. So I've gotten every non-zero element of C5, right? So 2 is a primitive root. So if I just look at powers of it, it cycles through every non-zero element. let's look at in Z7, if I look at the powers of 2, oops, and now I'm going to start over again, right? Notice the powers of 2 this time, 2, 4, 1. So that starts over. So it goes 2, 4, 1, 2, 4, 1, 2, 4. Not a primitive root because there's 6 non-zero elements. However, if you look at 3, when you square it, this is 9, which is 2 mod 7, and then 6, and then 18, which is 4, and then 12, which is 5, and then 15, which is 1. So 3 is a primitive root. Or in the field of 7 elements. It's really kind of a nifty thing that all finite fields have these primitive roots. That's actually, I saw something in a book. I was checking some of my facts on this, checking some other stuff, and somebody wrote somewhere, and one of the things I looked at, that the proof that every field has a primitive root is difficult. It is not difficult. It requires a little bit more technology than we have here, but it's not terribly difficult. Here's something that's difficult. Find the freaking primitive root, right? Notice how I guessed wrong in Z7. I tried 2. It didn't work out for me, so I guessed 3. If I walk up to you on the street and give you a large prime and say, find the primitive root, you know it's there, but computationally, it's difficult. And there is a problem. Yes.
So you're saying the primitive root, there is only one?
No, I'm not. In fact, if you look at, for example, 4, right? Because this actually requires 6 powers. If you look at 4, that'll also be a primitive root. In fact, these finite fields have more than one. But even finding one, like if I give you like a field of, let's say 103 elements, right, and say find the primitive root, you might get lucky right away, or it might take you a little while to do it, right?
You use quadratic reciprocity for that, right?
Well, actually, I'm going to actually get to that, the quadratic reciprocity. Good Lord willing, the creeks don't rise. But let me point out something here. Oh, yes, I was going to leave you with an open problem. There is an old conjecture dating back, if I remember right, I couldn't find a reference for this conjecture. There's a more modern one by Artin, but there was an original conjecture, I think, by Gauss. So that dates it by, like over a couple of hundred years. I think Gauss conjectured that for infinitely many primes, 2 is a primitive root. And the last status I know of that is that's still unknown. In fact, the best result I know is that for infinitely many primes, either 2, 3, or 5 is a primitive root. So finding these things or being able to write them down is difficult, but we know that they're there. So let us focus for a bit on ZP. And here I'm going to assume, when I say ZP for this talk, you can assume that P is odd. I'm going to avoid 2 because, as it is often said, 2 is the oddest prime of all. And for some of the stuff I'm going to talk about, 2 is a little bit degenerate. The non-zero elements, by what we've talked about so far, look like this. X squared, x cubed, x to the p minus 2, and x to the p minus 1, which cycles back to 1. And the reason I know this is I don't know what it is, but I know it's there. I can pick the primitive root x, and it has to cycle through all the powers. And of course, the last one it has to get to is 1, otherwise it's not a primitive root. All right. Now let me point out that if p is odd, which we've assumed, then the odd powers are not squares, and the even ones are, right? Of course, x squared is a square, and x4 is a square, and so forth. But notice p minus 1, if p is an odd power, or if p is odd, then p minus 1 is even, so you cycle back. That means that x itself cannot be a square, right? So the squares, I can sort of put a little, these are all squares, and the ones that I underline in blue, like this, and this, and this, are non-squares, right? And this is kind of an interesting thing, because what happens in a finite field, you've got finitely many elements. Half the things are squared, or squares, and half the things are not for an odd prime. You know, so what are you used to in fields? Well, in a certain sense, for the rational numbers, most things aren't a square in some sense of the word. That's not, from a set theory point of view, that's not really correct, but you know, one would expect sort of most things not to be squares. And the reals, things are squares if and only if they're non-negative. In the complex numbers, everything's a square. In the finite fields, you break it up into exactly two pieces, the squares and the non-squares. And this gives you the following theorem, right? And basically, you can tell whether a square, you can tell whether something's a square or not just by reading the exponent of the primitive root. If you got an even exponent, it's a square. If you got an odd exponent, it's not a square. And this gives us kind of a next result here. Theorem. If F is a finite field and A, B not zero, then AB is a square if and only if A and B are both squares, or both non-squares. Now this is kind of interesting, because if you think about what's going on back here, if you multiply two squares together, you get a square, and the square root is just the product of the two squares. That's not terribly surprising. What is perhaps a little bit more interesting is if you multiply two non-squares like x and x cubed, you get a square, right? For any pair. Now, imagine, for example, the rational numbers. Now, 2 is not a square in the rational numbers because the square root of 2 is not rational, and 3 is not a square in the rational numbers. However, well, and also if you look at 2 times 3, it's 6. 6 is also not a square in the rational numbers because the square root of 6 is not rational. However, for a finite field, if A and B are not zero, then the product AB is a square if and only if both pieces are squares, right? Right. This is actually kind of important, and I'm going to bring this up. Later. Somebody mentioned quadratic reciprocity, and I'm going to show you this. Let me. I'm truly not having a stroke here because there's a point to this. Let me also, while we're on the subject of squares, let me talk about quadratic equations, and I'm going to simplify this. Suppose we have a finite field. And let's suppose, I'm going to make it easy and suppose, let's say ZP, where P is not equal to 2. You want ZP, you want P to be odd here. You want the characteristic to be odd. And consider, pretend you're like in high school in the finite field world, and you have x squared plus ax plus b equals 0, and you want to solve this equation, right? Well, if you think about what you did in high school to solve this equation, they made you do this, you know, god-awful completing the square. And so you get x plus a over 2 squared. You rewrite the equation like this, plus b minus a squared over 4, right, 0. So I did my completing the square fast, but if you multiply that out, you'll see that, of course, you get x squared plus ax, and then you get a plus a squared over 4, which cancels with this one. You just got the b on the tail, right? This little trick always works over any field as long as what? There's something I did that you can't always do in a field.
You can't divide by 0, so long as 2 and 4, neither of them are 0.
That's exactly right. So the problem is you can't divide by 2 if 2 is 0. And so if you look at Z2, 1 plus 1 is 0. So that's a problem. Again, this is why 2 is very odd for quadratic equations, right? But that's why we're okay here, because I assumed that my P was odd, and so 2 is not 0, and so this is all kosher, right? But you're in trouble here if you're dividing by 2, right? And 2 happens to be 0. But if P is odd, which I assume, then this is solvable in the base field. And what I mean by that is, if you remember when you were in high school and you started doing stuff with the quadratic formula, you know, lots of your friends in high school probably melted down when you got a negative under the radical, right? But if you got a positive under the radical, you could solve it, and everybody felt all warm and fuzzy, because even though your answer had a square root in it, it was still a real number, right? And so that's what I mean. So under what conditions can you solve the original one? And that square root thing that you have to extract is in the original field. This is solvable if and only if a squared over 4 minus b is a square in the base field, we'll say in ZP. If that's a square, then you can take the square root of this. Well, after you take it over the other side, you can take the square root of that, and then you can add negative a over 2 to both sides, and you've got a nice, wholesome, all-American solution in your base field, right? So, for this reason and others, so determining squares in ZP is important if you want to solve quadratic equations, and also we'll see, as I promised in the talk, another application of this. And so there's actually a little tool, yeah, I guess I'll call it that. There's a notation that we use to sort of write this down. This is called the Legendre symbol. I'll give you a definition here. And this is just a little notation. So here we're going to pretend that our field is ZP. So we'll let P be a prime. We'll say an odd prime. And A is not divisible by P. So another way, if you're a huge fan of the fields that that you can couch this, is you can think of this as let P be an odd prime and let A be a non-zero element of Z mod P, right? So that's all we're saying here. We define, this is called the Legendre symbol. It looks like a binomial coefficient. AP, this is a symbol, and it barfs out a 1 if A is a square. And it gives out -1 if A is not a square. So it's like a little function that you plug in A for, and it returns the value of 1 if it's a square, and it returns the value of -1 if it's not a square. So it's just like a little, it's like a little detector, like a little radiation detector. It tells you if you've got a square in front of you or not, right? So here's some properties, and I can convince you that at least some of these are true for now. Number 1, anybody know this one? Well, under what circumstances would -1 have to be a square? Well, if -1, if you take a primitive root, right, for -1 to be a square, that means that the element 1 has to be a 4th power, right? So that means that however many cycles that primitive root has to go through has to be divisible by 4. If and only if P is equivalent to 1 mod 4. So for example, let me do a little quick example here. In Z5, we have something like I, right? Because -1 is equivalent to 4 mod 5. So 4 is the same thing as -1, right? Because when you add 4 and 1, you get 0 in Z5. And -1, 4 is 2 squared. But in Z7, -1, 6 is not a square. And that one is really kind of obnoxious because you have to, I mean, you have to go through and check, right? How do you know? I mean, basically you have to go through half of them and check things. But here are some properties that are even more sort of elementary, easier to see. 2, if A and B are the same mod P, so they're the same element in ZP. So for example, in Z mod 5Z, 2 and 7 and 12 and 17, they're all the same thing. Then the symbol AP equals the symbol BP. This seems very obvious because A and B are the same thing, and the proof is pretty easy. And here's a big one. So it's a character. That's a big one right there. ABP is ABPB. So the function behaves multiplicatively like that. And let me give you an explanation for this. Do you guys remember this result that we had back here? If F is a finite field, then AB is a square if and only if A and B are both squares or both non-squares, right? And we argued that because of the powers of the primitive root. Well, let's suppose that A and B are both squares. Then this symbol here is, if they're both squares, then the symbols are both 1, and AB is a square, so we get 1. If they're both non-squares, the symbol is -1 and -1, and -1 times -1 is 1, but see, the result said that that's a square. Now, if they're mixed up, if A is a square and B is a not square, then one of the symbols is, here is 1 and 1 is -1, and so the total symbol is -1, which is a non-square. It's exactly what the theorem says. Everybody okay with that?
For some reason, this is making me think about primes and rings.
Yes. Well, actually, there's generalizations of this to other rings as well, but we can talk about that in a bit. And here, this theorem, I think, is to number theory what the fundamental theorem of calculus is to calculus. I mean, this is a freaking miracle. And when I write it down, you may not see the utility of it, but I'll give you an example that shows theorem. And I'm going to write out this is called quadratic reciprocity. Let P, Q be odd primes. One. I've got problems with evens, so I'm going to take care of 2 first. The question is, when is 2 I'm not going to prove this here. I'll just state this as a fact, but it's not too difficult to prove. When is 2 a square mod P? 2P is 1, that is 2 is a square mod P if P is equivalent to 1 or 7 mod 8. And it's not a square if P is equivalent to 3 or 5 mod 8. And finally, this is the famous part of quadratic reciprocity. What about PQ? PQ is the same thing as QP multiplied by the correction factor of -1 to the P minus 1 over 2 times Q minus 1 over 2. That is a freaking miracle because this tells you the relationship. Under what conditions is the prime P a square mod Q? It's almost the same as if Q is a square mod P if you know this correction factor, right? This is amazing. And actually, this is one of the most proved theorems in the literature. I think there's something like over 105 proofs of this in the literature. But I'm not going to prove it because it'll take too long. But let me give you an example of why this might be useful. I want to know whether 3080 is a square or not a square mod 8675309. And who can we turn to? Not Jenny this time. We have to turn to quadratic reciprocity. And yes, 8675309 is indeed a prime. Okay, look, get on your horse and go do this, right? I mean, write down every number from 0 to 8675308, square them all, and see if it's equivalent to 3080 mod 8675309. Good luck with all this. Yeah, it'll take you a while. So the first thing I'm going to do is I'm going to factor 3080, which is actually 2 cubed times 5 times 7 times 11 mod 8675309. Now, by one of our properties of the symbol, this is 2 cubed P. So here, for notation, P equals 8675309, because I'm tired of writing it. 5P, 7P, 11P. Okay, that's one of our properties. And notice now what I have is I've got that symbol broken down into prime over prime, except for the first one. And this is 2 squared p, 2p, 5p, 7p, 11p. Does anybody see a way that I can simplify this?
Flip them upside down.
Right, right. Well, the first thing though is let me point out that this one right here is a 1. Because 2 squared is a freaking square. It doesn't matter what p it is, that's a square, so that's a 1. I'm going to toss it, right, because it doesn't affect anything. Agreed?
Yeah, I agree with that.
And 2p, if we look back at quadratic reciprocity here, let's see, we need to know what 8675309 is equivalent to mod 8, but if that was just 8675300, right? I mean, well, what is it equivalent to mod 8?
That'd be 1, right?
What's that now?
It'd be 1, right?
Actually, I think that I don't think so.
Because you get it's a multiple of 100 at the end. So well,
No,
Yeah,
that's
you're off
right.
by a little bit, but
four.
the 3 is
Yeah.
odd. Right?
3. So 300. It'd be 5.
Well, all you got to do is divide that thing by 8 and see what the remainder is, right? Mod whatever. So
It's 5.
that is correct. It is 5.
That's right.
So what is the status of this? So by quadratic reciprocity,
-1.
it's -1, right? So that's -1, right? And let me point out that 8675309 is equivalent to 1 mod 4. And that's going to be useful to us because when we do all this flipping here, notice the 8675309 is equivalent to 1 mod 4. So this is going to be even, correct? And so it doesn't matter whether this is even or odd, you're going to have an even power of -1. So the quadratic reciprocity says that I can do my flip willy-nilly. This is -1 times P5, P7, P11. I'm lucky in the fact that I don't have to really think about the other primes because since P is equivalent to 1 mod 4, then the power of -1 is going to be even. Everybody okay with that? So what do we get? This is -1. Let's see. So now I've got to take 8675309 and reduce it mod 5. That's 4 mod 5. And mod 7, I believe I got 6. And mod 11, I believe I got 5. And see, now figuring those separate things out is easy. This is a square. So that's 1. So I get -1 times 6, 7. And I'll do reciprocity one more time. 11, 5. Because again, 5 is equivalent to 1 mod 4, so I can just flip it. So this is -1, 6, 7, and this is 1 mod 5, so that's 1. So it's -6, 7, which is -1 times -1, which is 1. So this is a square. Everybody okay with that? So in particular, there exists X such that x squared is equivalent to 3080 mod 8675309. But, you know, good luck finding it, because it'll take you a while. I mean, if you've got a computer, you can do this pretty quickly, I guess. But all you have to do is make the prime bigger and bigger, and it's more and more difficult. Okay. All right. Let me give you an example. Let's see, x squared minus 10y squared equals 3 has no solution. This is another reason why we might care about things being square and quadratic forms. Now, if you start mucking around with this a little bit, you might think, well, maybe I can do it, right? I mean, because this is a difference here, and so I can pick some large x and some maybe 10 times some other large square y, but a little smaller square to get it to kind of balance out, and maybe I can get 3 out of it. You can't. That is, consider this. If you consider this in Z5, any solution in the integers should give you a solution in Z5, and this becomes x squared is equivalent to 3 mod 5. Because notice, the 10y squared goes the heck away, because 10 is the same thing as 0 mod 5. Right? And all of a sudden, you get this much easier thing here. And actually, you can check. I haven't done this yet, but I'll exhaustively check x squared 0, 1, 2, 3, 4. Mod 5, the squares are 0, 1, 4, 4, 1. There is never a 3 in the right column. So there's no solution to this at all, mod 5. That is, 3 is not a square, mod 5. So the original equation in the integers can't possibly have a solution. This is actually a very interesting and fun technique for throwing things out. Now, we're almost out of time, so I'm gonna give you a couple of fun ones for the road here. If you look in ZI, this is a set of A plus BI, where A, B, integers. Now, I'm going to give you some facts here that I obviously don't have time to prove. This ring here, this is called the Gaussian integers. It's sort of like the complex numbers, except instead of the reals, we've got integers here. This actually has the fundamental theorem of arithmetic, just like the ordinary integers. That is to say, everything can be written as a product of primes. Any prime p not equal to 2 can be written, well, actually, let me state it this way, is either a prime in ZI, so it remains prime, or it is written as a product of two smaller elements that are conjugates. And this depends on whether ZP has the square root of -1 or not. So for example, in Z5, -1 equals 4 equals 2 squared. So there's a square root of -1, and 5 in the Gaussian integers can be written as 2 plus I times 2 minus I, right? n z3 minus 1 is not a square. So 3 remains prime. And the reason, I mean, and it's basically because this is what we call a quadratic extension, but if you have, if your z mod p has a square root of -1, then it breaks up like this. And if it doesn't, it just remains prime. And so that gives us an interesting, and we know that ZP has square root of -1 if and only if P is equivalent to 1 mod 4. In this case, P is equal to N plus Mi times N minus Mi in the Gaussian integers. It breaks down into these two smaller ones, just like 5 was 2 plus I times 2 minus I. Therefore, P equals N squared plus M squared. So P is a sum of two squares if and only if P equals 2 or P is equivalent to 1 mod 4. So those are precisely the primes that can be written as the sum of two squares. So I will give you one more little kind of fun. See if you can use that. You can actually use that. I'm not going to show you, but it's pretty easy to figure out from there. You can tell exactly which numbers n greater than or equal to 1 are actually the sums of two squares. In a certain sense, it's almost kind of half of them. But let me give you this is called Pell's equation. This last thing is just kind of a fair warning for the road, because this technique is often very good at showing when you can't find a solution, just like we did back here for that equation x squared minus 10y squared is 3. We showed there's no solution there. How many of you think that's got a solution? Integers x and y that make this work. Oh, there is one silly solution. One is x is plus or minus 1 and y is 0, right? Everybody with me on that? That's the solution, right? But I'm going to call that the stupid solution. Is there a non-stupid solution to this?
If I recall, there is, but I don't think it's a very pleasant one.
Right. It turns out equations like this with the one is special, always have a solution, as a matter of fact. With some values of the number here, it's easy to find, some not so easy. This one is not so easy. The smallest solution, not plus or minus 1, 0, is 1,766,319,049 for x and 226,153,980 for y. Now, of course, if you reduce this equation mod 61, what you'll get is x squared is equal 1, and that's always got a solution plus or minus 1. And if you sit down and try to muck this out on a piece of paper, you'll quickly sort of convince yourself that you can't find any solutions. However, that's the smallest solution, and there are infinitely many, because in some sense the solutions multiply together and they cycle forever. So there's infinitely many solutions to this. Okay, this old timer does ramble on. That's it. Anybody have any questions?
So if you were wondering, 3,854,959 squared mod 8675309 is 38.
So you mean you put your picture up and went and figured that out for me? You need to email that to me so I can have that handy for my next talk.
It's in the chat.
Oh, okay. It's in the chat.
Yeah, it was a really short Python script.
Listen to that. Oh my goodness. Yeah, I'm too old school for that. Well, thank you
You're
very
gonna have
much.
to teach
Pete.
me Python.
Okay, other questions? Well, listen, stay tuned for next week. Felice will be talking, so you will get a better talk and a better class to speak. But in between now and then, you guys have a great weekend, and I hope to see you all next week.
Enjoyed it.
Thank
Thank
you.
you, Jim.
You're welcome.
Thank you. Thank you, Jim.
Sure thing. See you guys.
See you. Have a good weekend.
You too.